Welcome to this video on Singlet and Triplet Exciton transfer integrals with Fragment Orbital Constrained DFT. We'll be using the Amsterdam Density Functional Program, ADF, to calculate intermolecular transfer integrals based on Fragment Orbital Constrained DFT. These integrals are important for modeling exciton transport with methods like Forster and Marcus theory. An exciton can hop between two nearby molecules, moving from a state where one molecule is excited and the other is in its ground state to the opposite configuration. Fragment Orbital Constrained DFT is well suited to build these diabatic states because it constrains charges or spins on molecular fragments. In our case, we'll study pyrene dimers at different distances and orientations, similar to the models used in the paper by Venner and Baumeier. To capture the correct ordering of excited states in pyrene, we'll use the CAM-B3 lip functional, following the work of Grafe and Martens. The calculation starts with optimized pyrene molecules at a distance of 3.5 angstroms, typical for pyrene crystals. Each molecule is defined as a fragment, and FOCDFT is enabled so that localized excitations can be placed on each fragment. For excitations, we choose the triplet state only, using the TDA approximation and one excitation per fragment. For singlet transfer integrals, the same procedure applies, except with singlet states. The main calculation settings include the CAM-B3 lip functional, a TZP all-electron basis set, no frozen core, and good numerical quality. This ensures charge transfer excitations are treated accurately. After saving and running the job, we look at the output file. The electronic coupling between diabatic triplet states is about 0.17 electron volts. Repeating the calculation at different distances shows how the transfer integrals decay as the molecules move apart. Results can be obtained for the lowest triplet state, as well as the dark and bright singlet states. Changing the relative orientation of the molecules also affects the transfer integrals, and this can be explored in the same way. The approach isn't limited to dimers. It can also be applied to larger systems, like trimers of pentacene molecules, with environmental effects included through COSMO or explicit molecules using DRF to better mimic the crystal environment. For more details, check the SCM documentation and tutorials, where you'll find examples, explanations, and references to the literature. Thanks for watching, and be sure to explore our other videos on computational chemistry solutions.